Okay, so now we get to take a look at what happens when we solve matrix equations. So what I mean by matrix equation is when I have a matrix times a matrix equals another matrix. So here again, a capital X denotes a matrix. Well, luckily this situation is pretty easy to extend from our previous problem because we're essentially solving the same system of equations with several different right-hand side vectors. That's the columns of B. So let's take a 2 by 2 example to get a feel for this. So here we have a matrix equation, and we're going to dissect this into two different systems of equations. So we can write the matrix A times the first column of X is equal to the first column of B, and the matrix A times the second column of X is equal to the second column of B. Again, 3, 4 is the first column of B. 3, 5 is the second column of B. Sorry about that. And so the augmented matrices for these two systems would look like this. So they both have the coefficient matrix A on the left-hand side, and they just have two different right-hand sides, the first and second column of B. Now it's important for you to see that this setup is indeed true. It may help you to write out the four equations that are always represented by a 2 by 2 matrix problem, like we did in a previous lecture, and then pair together those groups of equations that make these systems here, because it's the same system with different right-hand sides and different unknown quantities. Let's make that clear too. Okay, so we have two different augmented matrices with the same coefficient matrix. So when we approach these two different systems and we start performing Gauss-Jordan elimination, how are the row operations going to differ between this matrix and this matrix? If you think about it, they're not, right? The same row operations will be used for each of these two matrices, because remember, the row operations really operate only on the left-hand side coefficient matrix, right? We find the pivots, we eliminate the values below it and the values above it. So we're going to perform the same row operations for each of these matrices. The only thing that's going to be different is how those row operations affect the right-hand side vectors. But there's no use in going through the entire process on both matrices. What we want to do is go through it once and keep track of those row operations and how they affected both right-hand sides. So it's possible for us to do that just by creating a larger augmented matrix. So we have a larger right-hand side. Then we can perform the row operations on both of these right-hand side vectors at once. So let's try this. So the first thing we're going to do in Gauss-Jordan elimination is eliminate this 2. So we're going to take row 2 minus 2 times row 1. So that gives us a 0 here. We have minus 1 minus 2 is a minus 1. And then we go on to the right-hand sides. So we'd have 4 minus 2 times 3. So 4 minus 6 is minus 2. And 5 minus 6 is minus 3. And then we can change this pivot element from minus 1 into a 1. And all we have to do is multiply the second row by negative 1. And that makes all these numbers positive. And then finally, we can eliminate the element above that pivot by taking row 1 and subtracting row 2. So now we have a 0. 3 minus 2 is 1. 3 minus 1 is 2. And we're done. We've reached a point where the left-hand side of the augmented matrix is the identity, which is always our goal. So now what we have to do is remember what situation we came from. And so now we have the equivalent system where the identity matrix times that whole matrix of unknowns is equal to this right-hand side here. So we've transformed our matrix into this, transformed our system into this triangular or diagonal system. So what does this mean? Well, this is the identity matrix. If I multiply anything by the identity matrix, I just get that thing in return. So we can conclude that that X matrix is equal to what was left here on the right-hand side. And thus we have solved our system. This method is particularly useful when we're trying to find the inverse of a matrix. Now, for any square matrix, if the inverse exists, we know that it satisfies this matrix equation. A times A inverse is equal to I. So just like before, we had an unknown, because we don't know the inverse, we'd like to find it, some unknown quantity x equals b. Only here our b is an identity matrix, and our unknown is an inverse matrix. So we can use that Gauss-Jordan method with multiple right-hand sides to solve for this inverse, this unknown quantity. So we start out with the matrix A on the left-hand side of the augmented matrix, right? We start with the coefficients on the left-hand side. And the matrix I on the right-hand side, right? The right-hand side of the matrix, which normally we'd see a B here, is an I. And then we're going to perform Gauss-Jordan elimination. And you'll remember that one of the things that tells us if our matrix has an inverse is that we can take it, perform Gauss-Jordan elimination, and transform it into the identity matrix with a pivot in every row. So if we can do that, then whatever's left over on the right-hand side is going to be the inverse matrix, which is the unknown that we were looking for. Just like here, once we transformed the augmented matrix so that the identity was on the left, the unknown matrix X was on the right. So here, once we get the identity on the left, our unknown A inverse will be on the right. If it's not possible to convert A to the identity under Gauss-Jordan elimination, then A does not have an inverse. So let's try this. Let's try to find the inverse of this matrix A. So we'll first set up the augmented matrix, where we have the matrix A, which is like the coefficient matrix here, and the right-hand side, which is the identity matrix. And we want to know the unknown, which is A inverse. What do I multiply this matrix by to get the identity matrix? And then we just perform Gauss-Jordan elimination. So we start with the first pivot element. We've already zeroed out, or we haven't, but the element below it is already zeroed out. And so we want to zero out the bottom left-hand corner here. And so to do that, we multiply the first row by 2 and add it to the third row. And so we have 2 plus 2 minus 1 plus 4 is 3. And 0 plus minus 2 is minus 2. And then continuing over on the right-hand side. So 0 plus 2 is 2. And then 0 and 1 don't change. Okay, and then rewriting this matrix on the right down here, we want to change our pivot element to a positive one, so we multiply this entire row by -1. And then we work on the next pivot element and trying to eliminate the row below it. And so you can proceed with these operations. You might even want to pause the recording now and continue through with these operations and see if you can reach the same result that we're about to. So again, eliminating this row, rewriting our matrix, we have a new pivot element, so we're going to eliminate the entries above that pivot element. Now we're starting with Gauss-Jordan elimination. working above. And always remember to keep your operations going through the entire right-hand side matrix, as those things start to change. And then once that's done, we're going to change this pivot element to a 1 and eliminate the values above it. And finally, we've completed our task. Once we have the identity matrix on the left-hand side, then whatever's over here is the inverse of the matrix A. So A inverse is just this matrix here, 1, 1, 1, 2, 2, 1, 2, 3, 1. So now you can try to work through this calculation by yourself. Use the same method to determine the inverse of the matrix B. If you went through that calculation, and you may have noticed that this is exactly the inverse we just calculated in the previous example. If B is the inverse of A, then A is also the inverse of B. So you should reach the solution that's the matrix we started with in the previous example. Now let's look at the inverse of a diagonal matrix. A full rank diagonal matrix is one that has no zero diagonal elements, and it has a particularly neat and tidy inverse, and one that we'll use quite frequently in this course. So let's look at an example. Here's a diagonal matrix. So again, what we're going to do is set up the augmented matrix with the matrix D on the left and the identity matrix on the right. So now Gauss-Jordan elimination is relatively simple because the elements below the pivots and above the pivots are already zero. So the only thing left to do is to transform the diagonal elements into ones. And we do that by dividing the rows through by the values on the diagonal. So the first row will divide by 3. The second row will divide by -2. The third row will divide by square root of 5. And so we're done, right? The left-hand side is the identity matrix, and the right-hand side gives us the inverse of D. So the inverse of D is just the diagonal matrix with the inverse of the individual diagonal elements. And you can see just through this process that this will always be the case. As long as D does not have any zero elements on the diagonal, right? A zero element on the diagonal would be bad. We can't divide by 0. So as long as these are all non-zero on the diagonal of D, then the inverse matrix is just the matrix that's 1 divided by all of the diagonal elements.